Good evening, West Yorkshire. A pleasure to be with you again. I'll not keep you too long from your clear skies. This is Keeping an Eye on the Universe, and as you can see from the subtitle, I'll be having a look at what various telescopes can tell us about what's going on in the universe. So we know that telescopes have been around for a long time, 400 years or so since Galileo first turned his telescope on the skies and started to record what he saw. And of course, telescopes have come a long way. In the last 100 years or so, we've seen telescopes changing from essentially using lenses to collect the light to essentially, these days, always using mirrors. Here we have the 2.5-metre Hooker telescope at Mount Wilson and the 5-metre telescope, the Hale telescope at Palomar Mountain. And of course, we're now used to the idea of having telescopes above the Earth's atmosphere. The Hubble Space Telescope has been with us for over 30 years now, and more recently has been joined by the James Webb Space Telescope, launched in 2021. There's been this continuous drive for larger and larger telescope apertures. Larger apertures mean collect more light, so seeing fainter objects, and the larger apertures also mean better definition, seeing more detail, and hence seeing more detail in some of these fainter, more distant objects. And that drive to larger apertures has by no means stopped. In a few years' time, we'll be seeing coming online, perhaps 2027 or so, the European Extremely Large Telescope. This drive for aperture has been around, well, since the beginning. You could argue for all of the last 400 years. This chart tries to encapsulate the last 100 years or so. In the top left, all of these telescope lenses or mirrors, most of them mirrors, are all shown to scale, with the Yerkes 1-metre or 40-inch lens in the extreme top left, and then the telescopes that I've just been showing you, the Hooker telescope, the Hale telescope, shown in the top left there. So you can see that telescope mirrors are getting larger and larger and larger. Especially now that we've changed to segmented mirrors, there's almost no limit to how large we could make a mirror. The record holder at the moment is that one at the top, the Gran Telescopio Canarias, the largest telescope in the world with a mirror, I would say diameter, but of course it's not circular, so it's a collection of hexagonal segments, nominally 10 meters or so in diameter. If we compare with the space telescopes, they're shown in the bottom left-hand corner, Gaia, Kepler, James Webb and Hubble. Kepler is being decommissioned, the other three are still in operation. You can see that the Hubble Space Telescope has a very modest size mirror. The 2.5-metre or 2.4-metre diameter Hubble mirror is similar in size to the Hooker telescope. The James Webb telescope here in the bottom left, substantially larger, because it's a segmented mirror, which is easier to make in larger sizes and indeed easier to get above the Earth's atmosphere. So there can be fewer iconic scientific instruments than the Hubble Space Telescope. Launched back in 1990, it's been operating for more than 30 years now. It's had a few technical problems in its time, but hopefully it'll be operating for another 5 years, maybe even another 10 years if the instrumentation in the next few years doesn't fail. And of course, the Hubble has been producing some wonderful images for decades. One of the most iconic images it's taken back in the 1990s was the Hubble Deep Field, pointing at a patch of sky and exposing for as long as possible, approximately 10 days or so, showing that a blank patch of sky isn't blank, it's absolutely full of thousands of galaxies. And bearing in mind the field of view of the Hubble, we can get an idea by taking an image of the moon, and there to the same scale is the field of view of the Hubble Space Telescope, that red rectangle there. So you can see the field of view of the Hubble is only a few arc minutes in size, and therefore it's only looking at a really small patch of sky, about the same as a grain of sand held at arm's length, or perhaps a grain of rice held at arm's length. So if we look in a deep field and we see thousands of galaxies, this is another deep field taking a little bit after the first one I've shown. If we can see thousands of galaxies in this small patch of sky, then we can extrapolate up and assume that if this is representative of the whole universe, as best we can tell it is, then we can deduce that the observable universe must be full of many hundreds of billions, perhaps a few trillion galaxies. So back in the 1920s, it was argued whether or not the Milky Way was the only galaxy, whether or not these spiral nebula were inside our galaxy, but it turns out they were actually external galaxies, thanks to the work of Edwin Hubble, who showed that these various spiral nebula were galaxies in their own right, some of them very remote from us. So that's one of the things that the Hubble Space Telescope has done for us. It's given us a sense of perspective, making us realise that the Milky Way in which we live is only one of perhaps a trillion galaxies that we're capable of observing. Some of those galaxies are, of course, closer than others, and for some of the closer galaxies, the Hubble Space Telescope has given us an exceptional view, an exceptionally detailed view of these galaxies. So we can not only see the general structure of the galaxies, we can look in detail at star-forming regions and get an idea of how these galaxies came to be and how these galaxies have evolved. It's become clear from the last few decades that most galaxies do not live in total isolation. It is very common to find galaxies are interacting with their neighbours, as indicated by this pair, the rose galaxies, where the spiral structure of the galaxy above is being distorted by the galaxy below, and probably vice versa as well. It's clear that galaxy interactions are not only common, they seem to be an essential part of galaxy evolution. Here we see the core of the antenna galaxies, so called because of large tidal tails which are extending beyond the range of the Hubble field of view here. So we're looking at the core of these two galaxies colliding, and the red areas indicate that there's a riot of new star formation because of this galaxy collision. So far from being the end of life of a galaxy, when galaxies collide, it can actually trigger new star formation. As I say, an essential part of galaxy evolution, not the end of life of a galaxy. Looking within our own galaxy, the Hubble has been able to give us wonderful views of this, for instance, is a planetary nebula, the Helix Nebula in the constellation of Aquarius. This is the end of life of a star of a mass similar to our Sun. So in a sense, we're looking at what our Sun is likely to become in a few billion years' time. When our Sun runs out of its fuel, hydrogen, it's going to swell up into a red giant, eventually lose the outer atmosphere, and that will then slough off to produce a planetary nebula such as this one. And what's left right at the core will be a white dwarf, which is again the ultimate fate of our Sun. The star right at the centre there, a white dwarf with a beautiful planetary nebula around it. More massive stars won't end their life in quite the same way. If they're massive enough, they could end in a supernova. And this rather nice Hubble view of the Crab Nebula, a mosaic because it's a relatively large feature on the sky. This mosaic shows the intricate nature of the nebula that was produced by the supernova that went off about 1,000 or so years ago, as seen from the Chinese civilization here on Earth, 1054 AD. Images like this have enabled us to get a better handle on what happens in a supernova, what elements are produced, as well as the interstellar medium into which this material has been thrown out by the supernova. But of course, the most iconic picture, rather than the Hubble Deep Field, as far as most people are concerned, are the pillars of creation, imaged with each of the cameras that was fitted to Hubble. The space shuttle allowed astronauts to change the cameras every few years, and this is the result of the third camera imaging the pillars of creation, which again were originally imaged in the 1990s and then re-imaged for its 25th birthday. So not only does, again, this give us a good indication of what's going on in star birth, because we think this is a stellar nursery and the pillars are being carved out by the radiation from hot young stars that are radiating but can't necessarily be seen. This highlights one of the limitations of the Hubble Space Telescope, in that it is unable to see through a lot of the gas and dust in regions such as this. When stars are in the process of early formation, there is so much gas and dust around that it's often very difficult to see exactly what is going on. So if we do want to see how stars are born, and in particular how planetary systems form around new stars, we need to be able to see inside structures like this. And that's one of the reasons that it was decided to go with a new space telescope after the Hubble had been in operation for a little while. Plans were already being made for a new generation of space telescope that would work not in the ultraviolet and visible part of the spectrum, but well into the infrared part of the spectrum. And hence the James Webb Space Telescope. It took a long time to get it into space, simply because it's a very technically challenging thing to do, and it turned out to be rather expensive and rather time consuming. They got there in the end and launched it in 2021. It operates in the infrared, partly for the reason I've just said, because with infrared we can start to look inside the star-forming regions and the planet-forming regions, which are very dusty and tend to scatter a lot of visible light. So the James Webb has got a much larger mirror than the Hubble Space Telescope, shown in the bottom left there, with a diameter of 2.4 meters. The James Webb is a lot larger, but it's working at longer wavelengths, and so the resolution, the amount of detail we can see with the James Webb, is comparable to the amount of detail we can see with the Hubble Space Telescope. But with a telescope this size, the size of the Hubble was limited by how large a telescope you could get into the cargo bay of the space shuttle. But with the James Webb, they decided to go with a segmented mirror, and that meant folding it up in order to make it small enough to go onto the top of a rocket and be launched into space. So there it is on the left being tested, and then folded up like a piece of origami in the middle and launched on Christmas Day 2021. Unlike the Hubble, it's not in Earth orbit. It was sent off to a particular location, L2. L2 is a sort of parking point in space, and that particular point is favoured for a number of different telescopes. They're not actually sitting at the L2 point, they're actually orbiting around the L2 point, but that point sits about 1 million miles above the midnight point on Earth. So there's the Earth and the Sun. Clearly the point on Earth closest to the Sun is where we have local noon, and local midnight is on the opposite side. And L2 is just hovering 1 million miles above midnight. So well beyond the orbit of the Moon, not quite to scale this particular diagram. So each of these red dots effectively indicates a point where you can park a spacecraft. L2 was considered optimum because, as seen from L2, the Moon and the Earth and the Sun are all in the same direction, and so a single large sun shield could actually shield the James Webb from the heat of the Moon and the Earth and the Sun. And given that the James Webb works in the infrared part of the spectrum, it was rather important that all of its instrumentation was allowed to cool down, and hence it needed to be shielded from the heat of the Earth and the Sun in particular. The second reason for going for infrared, apart from the fact that allows the James Webb to see star formation and planet formation, is that by working in the infrared, it's able to see more distant parts of the universe. The universe is expanding, and hence light from distant parts of the universe have been stretched. In particular, some visible light from very distant galaxies has been stretched and its wavelength increased until it's now no longer in the visible part of the spectrum, but now in the infrared part of the spectrum. And hence, in principle, the James Webb should be able to see more distant galaxies and hence see further back in time because of the finite speed of light. If we look at this timeline, there's the Big Bang, the start of the universe back at time t equals 0, and there's us here and now 13.8 billion years later on the right. The numbers in red indicate how much the light will have been shifted if it left an object at a particular time in the past, and this indicates where in the past we're talking about. For instance, if we look at an object from 5 billion years after the Big Bang, it would have released some light which then got stretched on its way to us, and it would have been stretched by a factor of 2. We call that a redshift of 1. The stretch is equal to the original wavelength. The furthest back you can hope to image anything without using a telescope, I have found, is about here, z equals 4. In other words, as a COVID lockdown challenge, I tried imaging a distant quasar, a galaxy with a very bright nucleus. I tried imaging one of these with a camera and lens, but without using a telescope. And I got back to this point here, a redshift of 4.1. That corresponds to about 1.5 billion years after the Big Bang. And it also means that because of the expansion of the universe, the quasar in question at that particular point will have been receding from Earth at twice the speed of light. That's quite an amazing fact. As soon as you go beyond about this point where the cursor is, about 4 billion years after the Big Bang, the redshift is about z equals 1.5. And from that point further back, all of the galaxies will be receding from us faster than the speed of light because of the expansion of the universe. So you could say that most of the galaxies seen by the Hubble Space Telescope indeed are receding from us at those sorts of speeds. But although that's interesting, the Hubble and the James Webb really weren't designed just to go back to this sort of time. What we really want to do is to go back to this first billion years or so, because that's when we think the first stars and the first galaxies were born. And we don't know exactly when. Let's just blow up those first few 100 million years to make it a little easier to see. So here again we have the Big Bang, and now we have a few 100 million years after the Big Bang. And again the redshifts, the light stretched by a factor of 10 or 14 or 30. So we think after the Big Bang it took a little while for the first stars to form. It only took 3 minutes to make all of the hydrogen, but it would have taken, we think, hundreds of millions of years for the first stars to start shining. But when did that happen? Well, Hubble has been able to look back as far as a redshift of 10, which corresponds to seeing back to the early universe around here, about 500 million years after the Big Bang. It is hoped that once the James Webb Space Telescope has been operating for a few years, it ought to be able to push that even earlier and ask the question, can we push that back to the point where we can see the very first stars, the very first galaxies? So far, we haven't got that far. Although the James Webb is pushing the limits, we are still seeing, even at the earliest times that we can currently observe, we're still seeing stars that have formed and galaxies that have formed and supermassive black holes that have formed even earlier than we would expect. And that's a little bit perplexing. I'll come back to that in just a moment. I'm not going to go through all that James Webb has shown us because although it's only been operating for 2.5 years or so, it has of course produced an enormous number of images and spectra. It has revisited a number of the objects that Hubble Space Telescope has seen. And one of the first on its list was the iconic Pillars of Creation. Notice that now we can see so many more stars compared to the Hubble picture, which only had a few dozen stars in this field of view. Now we can see hundreds, if not thousands of stars, because the James Webb, working in the infrared, is able to penetrate some of these dusty regions that would otherwise be scattering visible light quite substantially. When we look at planetary formation, again, we can see even more detail. Fomalhaut is a star system. Here the star itself has been blacked out with that black dot in the middle, and we see the dusty environment of this star. Again, it was earlier imaged by the Hubble Space Telescope, but with James Webb working in the infrared, we see more detail in what's going on around this star in the early stages of planetary formation. And we see structure in there. We can see a belt not only an inner belt, it looks like we see an outer belt as well, or an outer ring. It's tempting to think, is this solar system being formed in a similar way to our solar system? Are we looking at something similar to an asteroid belt here and maybe a Kuiper belt there? Tempting, but there's no evidence that we are seeing anything on quite the same scale, but it is interesting to see that we are seeing structures that we might be able to relate to our own solar system. And again, just like James Webb is revisiting some old Hubble objects, it's done the same with Pandora's cluster. This again was imaged by Hubble, but now we're imaging it with James Webb. We've got a mosaic here. So we're seeing a large number of objects over a reasonable chunk of sky. This was an image shown as the astronomy picture of the day back in the middle of last year. But this is notable not because it has higher resolution than the equivalent Hubble image, but because it's working in the infrared, it can see more distant galaxies. And you notice that a lot of these small red objects are very distant galaxies. We have some bright white galaxies that are relatively close to us, only a few billion light years, but a lot of these very faint red dots are very distant galaxies. It's been estimated in an image like this, a mosaic image like this, there might be as many as 50,000 objects that are capable of being analysed to see what we can learn about the galaxies and their redshifts. So a huge amount of data still to be analysed in images such as this. The James Webb has also revisited the Crab Nebula, which is interesting for a number of different reasons, not only because now in the infrared we can get different information about the chemical elements that made up this star, which is now seeding those elements back into the interstellar medium after this supernova, but we can compare it directly with the Hubble picture, which was taken about 20 years earlier. And if I flick between the two, this is the James Webb image, and that's the original Hubble image from 2005, a little over 20 years ago. Sorry, 20 years-ish ago. And if we compare the two, if I flick back and forward, if you concentrate on one particular feature, such as this one here, if I flick backwards and forwards, you can see there's a definite change of scale between the two images. That's not simply because one is visible and one is infrared. It's because if they're taken 20 years apart, and remember this supernova went off something like 1,000 years ago, 20 years is a few percent of that 1,000 years. And therefore we're seeing the nebula a few percent larger simply because it has physically grown from the original supernova 1,000 years ago. So we can learn a lot about the dynamics of the end of life of stars such as this by making comparisons between different telescopes. One of the relatively recent results from the James Webb, this was taken at the end of last year, or at least this was the astronomy picture of the day at the end of last year. This is an observation where again we're using telescopes in combination. This is the Pandora cluster yet again, but what's of interest now is what's going on in this small square right at the centre. And you might think it's the little white blob that's interesting, but no, that's a galaxy which might be interesting in its own right, but what's particularly interesting here is the very, very faint one inside the white circle here. Because when the X-ray telescope Chandra looked at the same area, it found a very bright object there. So this object is very bright in X-rays, rather faint in visible or infrared light, but there's definitely a galaxy there. And if the James Webb can see a galaxy, then it's capable of taking a spectrum of that galaxy and hence obtaining a redshift. And on doing that, the James Webb found that this galaxy has a redshift of 10. That puts it a long way back in terms of the early history of the universe, only a few 100 million years after the Big Bang. And yet it would appear that this galaxy, which is a very young galaxy, it can't be that old, already has what appears to be a very bright X-ray emission from its centre. So this is thought to be one of the first supermassive black holes ever detected. This supermassive black hole existed just a few 100 million years after the Big Bang, But the question the theorists have to answer now is, how can that be? It was thought a while ago that surely it'll take 1 billion years or so for stars to go through lots of generations in order to coalesce into a supermassive black hole. But that doesn't appear to be the case. It looks like supermassive black holes existed very early on in the universe, and that is perplexing a lot of theorists who are trying to come up with ideas as to how that could be. Coming back inside our own galaxy again, the James Webb is able to see through these very dusty environments, so now we're looking into the core of a stellar cluster being born, so-called protostellar outflows, meaning stars that are just in the process of being born out of the gas that we can see in an image like this. Stars are being born and producing these characteristic jets or outflows from lots of different objects within the cluster. And this particular image, although it's nice and aesthetically pleasing in its own right, is scientifically rather relevant, because an image like this is telling us that these outflows often are parallel in a star cluster. And given that we think the outflows are related to the way stars are spinning, that would indicate that when stars are born together, they tend to spin in the same direction. That was thought to be the case prior to images such as this, because if you have a cloud of gas condensing to form a whole load of stars, then the conservation of angular momentum would indicate the stars are likely to be born spinning in the same direction. But now we have observational evidence that indeed they do. So a rather important piece of evidence relating to star birth. And at the other end of stellar evolution, the James Webb has been looking at star death, at supernova, not to understand the details necessarily of how stars go supernova, but this extragalactic survey that's been carried out has identified lots of supernova in this one field alone. And what they're trying to do with this particular survey of supernova is try and figure out whether or not these supernova have the same intrinsic brightness. Because often it's been assumed that they are standard candles, and hence we can use supernova as a proxy for distance. Because if they are all the same intrinsic brightness and we see them at different apparent brightness, then effectively that gives us the distance to them. So it's important to know whether or not supernova do have the same intrinsic brightness, because if they don't, our assumptions have been incorrect, and that means our ability to scale the universe is perhaps flawed. So a very important piece of information. And one of the most recent results I could find was taken again, or at least presented in Astronomy Picture of the Day a couple of months back, where we have the galaxy. Again, you can hardly see it in the main image, but if we blow it up, this galaxy, the red blob here indicated by the white arrow, is the most distant galaxy yet detected. It has a redshift of 14. That means we are seeing galaxies in the process of formation. And where does that fit on our scale that we indicated before, with the Hubble going back to z equals 10, and we want to push the James Webb as far as we can? It looks like we have now seen galaxies back to z equals 14. That means this galaxy is being imaged as it was a mere 300 million years after the Big Bang. So it's not a very big galaxy, so that makes sense, because if galaxies form by merging and colliding with other galaxies, then we wouldn't expect very early galaxies to be very large. We would expect them to grow with time. So it's no surprise that it's not a very large galaxy, but it still surprised people that we do see galaxies at all as early as 300 million years after the Big Bang. And who knows how far we can push that. If James Webb continues to see fainter and fainter galaxies, perhaps we can push that z equals 14 even further to the left. But to find those targets, we're going to need survey telescopes, such as this one that will be coming online fairly shortly, the Large Synoptic Survey Telescope. now renamed the Simonyi Survey Telescope, but the idea of calling it the LSST, the Large Synoptic Survey Telescope, though that acronym has been used so much, they decided to keep the acronym even though they've renamed the telescope. So it's now the Legacy Survey of Space and Time. What it's going to be doing is, from its site on Chile, it's going to be trying to survey as much of the sky as possible. The intention is to survey the entire sky that it can see every 3 nights and continue to do that for years to build up a large database of all the objects that are out there. Tens of billions of stars, tens of billions of galaxies. That's the telescope. It's near completion. First light, I'm not sure what they're expecting, 2024, 2025, something like that. You can get an idea of the scale from the gentleman on the bottom left there. I assume it's a gentleman. So we've got an idea of what that is going to be doing. What sort of chunk of sky is it going to be looking at? Let's remind ourselves as what the Hubble Space Telescope could see relative to the size of the Moon. There's the Hubble Space Telescope field of view, just a few arc minutes in size. The field of view of the LSST is going to be huge. It's so large, in fact, I can't actually fit it into this particular slide. It's a circle of which you can see a tiny part of the circumference there. How do you build a telescope with such a huge field of view? Well, you start with a relatively large mirror. That's the 8-meter primary mirror before it was figured to shape. It's actually the first and the third mirror of a rather complex optical system, but you get an idea of the scale there. But a large mirror in itself is not what you need to image a large chunk of sky. You need to collect a lot of light, but you also need to make sure that you've got a huge camera. So how large is the camera that's used in the LSST? No, that's not it, but just for scale, that's the camera from a typical mobile phone. It barely is more than a few millimeters in size. It wasn't until recently that I realized that that is by no means the smallest size that you can build for a camera. The smallest one I could find is that size. It's basically the size of virtually a grain of sand. And yes, it is a functioning camera, but ignore that just for the moment. Let's think about the mobile phone camera and to scale, let's look at the chip that's in the Hubble Space Telescope. The chip is approximately 4 centimeters in size, 40 by 40 millimeters, and it's 16 megapixels. Perhaps not that impressive if you've got a digital SLR or mirrorless camera, which might have many, many megapixels, and a chip which isn't so much smaller than what we're talking about here, 40 by 40 millimeters. But of course, it's the quality of the optics, and for the Hubble, the fact that it's above the atmosphere that gives it such superb images. But let's take the Hubble chip as a starting point and say, how big is the detector in the LSST, the survey telescope? Let's start with that 16 megapixel chip in the Hubble, and let's imagine adding another 8 of those into a package. Let's take that package of 9 Hubble chips and let's duplicate them up and add another 8, and then another 12. And then a few more chips, which we're going to use for making sure that it's pointing in the right direction and guiding correctly. So the sensor in this camera is absolutely huge. It's 0.6 meters square. So large, I can't really show you exactly how large it is, other than to give you an idea of this is 1/4 of the whole of the detector. 3 billion pixels in total, and it can be read out in 2 seconds. It's rather important that it's read out quickly because it's going to take a series of 15-second exposure. It's not going to be looking at a chunk of sky and exposing for hours at a time. It's going to get all of the light it needs because of that large mirror in a single 15-second exposure. And I can't possibly show you what we would expect to see with a 3 gigapixel sensor because, of course, my monitor and zoom is incapable of showing you a 3 gigapixel image. So let me give you a taste of what's to come by just taking that little black square there and saying, if we were to take an image, what would we see if we just looked at that tiny part of the image shown by the black square? Well, we would hope to see many, many thousands of stars and galaxies in a single 15-second exposure. And remember, the actual image produced will be 3,000 times this area. It'll be taking 15-second exposures, read out in 2 seconds, maybe take a few seconds to move to a different patch of sky, and then repeat. And hopefully repeat all night, essentially every clear night, which is probably more than 300 nights of the year, for the next 10 years. So the amount of data coming out of this survey telescope is going to be absolutely huge. It'll be cataloguing tens of billions of stars and tens of billions of galaxies, and it will be finding out what's out there, including objects within our own solar system, because it's going to be catching thousands of objects either in the asteroid belt or trans-Neptunian objects, as well as looking at all the objects that don't change in terms of their position that much. So it'll be able to map out a very large chunk of the Milky Way, not every star in the Milky Way, but a very large fraction of them, and it will be able to see tens of billions of galaxies, looking at how they change night after night, if they change colour, if a supernova goes off, etc. It's been estimated that it will be able to see thousands of supernova every night. So far, throughout all of history, we've seen about 1,000 supernova across all of the telescopes that have been operating for decades and decades and decades. Once the LSST is operational, it'll see 1,000 or 2,000 supernova every night for the next 10 years. Along the way, hopefully we'll get a better feel for not only cataloguing lots of objects, but it might also help us answer the big questions of where is all of this dark matter and what is going on with dark energy. We know dark matter is out there. We don't know exactly how it's distributed. This is simply an artist's impression indicating that dark matter might be uniform or it might be clumpy. Along the way, LSST will help us answer those sorts of questions. And in a few years' time, we'll have these monster telescopes, these extremely large telescopes. You can get an idea of scale from the people on the gantry or standing just out the front there. The European Extremely Large Telescope with a diameter of 40 metres, and also on the way, hopefully, the 30-metre telescope on the top of Hawaii. With such a large collecting area, these telescopes ought to be able to see very faint objects and hence very distant objects, and should be able to follow up from whatever the LSST finds. So we said that there are lots of telescopes, all of which have different purpose. We've seen that the largest that we can expect in the near future is the Extremely Large Telescope. Is that the largest we can ever hope to build? Well, for the time being, yes, but there have been plans for what would it take to build a telescope 100 metres in diameter. Technologically, that would be a real challenge. It's bad enough with something 40 metres in diameter. 100 metres was thought at the time to be simply too much, too expensive and too soon, though there are still people who would like to see a telescope that size built. What would we call it? Well, we've already used the Very Large Telescope moniker, and we've already used the Extremely Large Telescope. So what would we call an object 100 metres in diameter? Well, some people have suggested the owl. Not because owls have large eyes, but simply because that would be the overwhelmingly large telescope. So, okay, astronomers are never good at labelling these things. But we have to remind ourselves that we need all of these telescopes, not just the large ones. We need the survey telescopes, like the Chamonix telescope in the Vera Rubin Observatory. That will be monitoring the skies and finding out what is out there. When we find interesting objects, they will be followed up by the Hubble Space Telescope or the James Webb Space Telescope, looking at these objects in more detail. And if the object is really faint, then we'll pass that on to something like the ELT. If it's really faint, we need a large telescope to pick up the light. Then the ELT will concentrate and look in detail at the objects found over the next 10 years by the Vera Rubin Observatory, the LSST. So we need these telescopes working in concert with each other. We need the survey telescopes to catalogue the universe, to find out what's out there and identify the interesting objects, which can then be passed to the space telescopes working above the Earth's atmosphere and to the large aperture telescopes to look at the really faint stuff. With all of these telescopes working in concert, we should be able to answer some of the questions we have about the universe. And perhaps more importantly, they'll be able to tell us the questions we haven't even thought of yet. Thank you for listening.